Hello everyone, welcome to the fifth lecture on operational amplifiers. In this lecture, we're going to learn about slew rate and then we will see briefly a peak detector op-amp. So let's get started. Slew rate is defined as the maximum rate of output voltage change per unit time. And this slew rate, it helps us to identify the amplitude and maximum input frequency which is suitable for an op-amp in such a way that the output waveform which is created out of op-amp is not distorted. So in general, we want slew rate to be high as possible to ensure that there is maximum undistorted output voltage we are obtaining. And if we talk about general purpose devices, then they have generally a slew rate of 10 volts per microsecond. And here, the slew rate for a 741 op-amp is mentioned, which is 0.5 volts per microsecond. So what does value indicate? This value means that no matter how fast your input voltage changes, the output voltage can change only as fast as 0.5 volts per microsecond, which is its slew rate. Okay. Now let's look at the op-amp 741 and so 741 op-amp, as you see at the input side, we are giving a sinusoidal waveform and we expect to get the sinusoidal waveform at the output also. But if you look at the right picture, so this waveform you see here, it shows two waveform A and waveform B. Waveform A is the expected output waveform from this op-amp, but what we are actually getting, we are getting waveform B. Now the question is, why are we getting waveform B? We are getting the waveform B, which is a triangular waveform, because the slope is the slope of the output sine waveform is greater than the slew rate of the op-amp. So you see this slope of the sine wave is greater than the slew rate of the op-amp. And however, the value is not given, so we can just assume that the value of the slope is greater than the slew rate. And if that happens, then the sinusoidal waveform appears to be triangular. And therefore, the slew rate distortion of a sine wave produces this triangular waveform. Now here, if you look at this particular formula, this is the formula for slew rate, dV by dt, rate of change of voltage upon rate of change of time, which is equals to 0.5 volts per microsecond. And this is for 741 op-amp. And if you are working with other types of op-amp, then this value may be different. So for example, for LT1363, it has a slew rate of 1000 volts per microsecond. So each op-amp might have different slew rate. So you can look into the data sheet to see what the value that particular op-amp holds. Now next is the power bandwidth. So there are two ways to avoid the slew rate distortion of a sine wave. The first thing you can do is you can use the op-amp with the higher slew rate value. Or the second is you can accept an output waveform with a lower peak voltage. So we will try to avoid the second option. If we have the option in the beginning when we are designing our project, we would choose an op-amp with a higher slew rate. So as you can see here in this waveform, this is my waveform B, this is my waveform A, the small one is the waveform A, and this big sine wave is the waveform B. And these both waveform A and B, they have same frequency. You can see the frequency is same, but they have different slope. Their amplitude is different. So you can see that for waveform A, so this is your small one is the waveform A. If at a 30-degree angle, so this is 30-degree angle, at this particular angle, your delta V, rate of change of voltage, is 0.5 volts. And here at waveform B, your peak value, here it is rate of change is a change of voltage is 5 volts. Okay, and the peak the peak value here, so this was your rate of change of voltage at 30-degree angle, and here this is your peak value for this waveform B, and for waveform A the peak value is 1 volts. So here we see the rate of change in voltage delta V for waveform B is 10 times than that of waveform A, and that we can easily see because this is 1 volts, waveform A is 1 volts, and waveform B is 10 times of waveform A. Okay, during the same interval, even with same frequency. So it is desirable to to choose the op amp with the higher slew rate. And if the slope of the output waveform is greater than the slew rate, then the op amp its output will be distorted. Okay, so now let's move on to next. The effect of slew rate on sinusoidal signal. So this is the sinusoidal signal waveform formula. V is equals to Vm sin omega t. Now if you take the differentiation of this first equation here, then you will get this dv by dt with respect to time. If you differentiate with respect to time, then you will get Vm into W cos omega t. Okay, so that's the formula for differentiation. When you differentiate this, you will get this value. Okay, Vm is the constant, but sine omega t, when you differentiate, you get W cos omega t. And when you take the absolute value of this dv by dt, you are left with Vm into 2 pi f. Okay, and this dv by dt represents your slew rate, so that's why we have written here slew rate. When this slew rate is greater than equal to Vm multiplied by 2 pi f, then there will be no distortion. So what does this represent? It represents your it represents your slope. Okay, slope of the input waveform. So and this is your slew rate, and then this Vm represents your peak value of the output sine wave. Now you can take the frequency to this side, and then or you can keep the frequency here and you take this term Vm 2 pi this side, then you will get a equation like this, where frequency is equals to slew rate upon 2 pi Vm, where this f max frequency is basically the highest undistorted frequency. So this represents your highest undistorted frequency, or you can say power bandwidth, which is equals to slew rate upon 2 pi peak value of the output sine wave. Okay, so this f max can increase by using an op amp with higher slew rate, because they have a proportionate relationship. So if the slew rate increases, then your f max value will also increase. Or by accepting an output waveform with a lower peak value, because they have the inverse relationship. So if this is lower, the peak value of the voltage is lower, then this f max will be higher. Now here, if you see this particular case where voltage is 10 volts and slew rate is given 20 volts per microsecond, then for 1 volts it will be equal to, so I'm taking this portion, and if you create like this, 1 volts will be equal to 1.20 microsecond. So we are going to see what would be the maximum uh, uh, what would be the slew rate for this particular 10 volts voltage. So if you multiply here by 10 volts and then 10 volts here as well, then you will get 0.5 microsecond. 10 volts, for 10 volts you'll get 0.5 microseconds, and that's your minimum distortion you can get with this value. Okay, now moving on to the next. This is a numerical problem, very simple problem. If the required output for the op-amp is 20 kilohertz sinusoidal signal with 10 volts peak voltage, find minimum slew rate of op-amp op-amp. So frequency is given in this question, and the peak voltage is given, or VM we can say, is your 10 volts. So simply just putting into this slew rate formula, we can find out the slew rate, where slew rate is equal to Vm 2 pi f. Vm is 10 volts, 2 pi, and then frequency is given, so you'll get around 1.257 volts per microsecond. So it should be second. I'm missing the S here. So, and then you can search this value online. What op-amp supports this slew rate? Then you will get the answer LF411. Okay, so that's the op-amp can support this slew rate. Now, looking at the second problem, find the frequency of the square wave pulse where the output will be triangular wave with peak value of 4 volts. So output, so we are feeding the square wave, and at the output we are expecting to get the triangular wave with the peak value of 4 volts, and the slew rate is given already, which is 2 volts per microsecond. Okay, so what do we have to find? We have to find the frequency. So case 1, when you want 4 volts triangular waveform, so using this slew rate formula, I am finding for 1 volts how much microsecond will be required. So you just so this 2 will go here, you will have 0.5 microseconds, and you multiply 4 on both the side, you will get for 4 volts it is 2 microseconds. So this 2 microsecond will be required for half period. So as you can see, for this half period and the other half period is 2 microsecond, and the total t on time will be 4 microseconds. Now, what if you want 10 volts of triangular waveform? So for that, you will pick this the same formula and multiply 10 volts on either side, and then you will get for 10 volts you require 5 volts for each period, half period. So you have 5 microseconds and 5 for so this is also for 5 microseconds. So total t on time will be your 10 microseconds. And using this value you can calculate the frequency, because frequency is the reciprocal of the time period. And similar to here, you got 250 kilohertz and here 100 kilohertz. So this was another problem. Now we will move on to the peak detector. So this peak detector circuit, they are used to determine the peak value of an input signal, and they can be used in different application. For example, in AM modulation and demodulation in communication system, they can be used. So here on this slide you see a very simple peak detector. I would say this is the ideal circuit for a peak detector, and on the left is the ideal waveform which shows and which is showing that the peak of the waveform is being detected. So what will happen in this, you have this input voltage V in, which is let's say when this is positive, then what will happen? When this is positive, then your diode will be forward biased, and when your diode will be forward biased, then this voltage will transfer to this capacitor, and then your capacitor will start charging up to the peak value of this input signal. And after the peak value of this V in, starts reducing, when this input voltage starts reducing, then what will happen, at some point this diode will go into the reverse bias condition. And during this time, this capacitor, its role is to hold the peak value of the input signal. And when the diode is forward biased again, when this input voltage increases and this diode is forward biased again, then this capacitor will charge to that new peak value, and then hold that value, hold the value, this capacitor hold that new value until the new value of Vin is received from the input signal side. So you understand like how it is, like how the diode forward biased, and then this capacitor charges to that value, and that's the current peak. And as you get the new V in voltage, then it goes to the it holds the value to the new input voltage. So here you have this signal, and this is the peak of the signal which is being detected. So here you can see, so for example, here your input voltage has gone down, but this capacitor will hold this value until a new value which is greater than this is observed. Now here the new value, input value, is obtained. So that's why you have this new peak, and so capacitor charges to this value, and then it will hold to this new peak value. So that's why you see that it is not dropping, because whatever the voltage you're getting below this is lower than this peak value. So this says capacitor charges to new peak value when diode forward biased again. So the same thing which I've explained. Now, if you want to accurately measure the circuit, then you can use the super diode along with this op-amp. So in this way, you can basically connect the circuit, and some finite amount of load you can connect like in this way to the output terminal. And because of this load, the capacitor which is here, it will discharge through this resistance. Okay, so you have load connected here. So if capacitor has to discharge, then it will discharge through this load. And now if you see this waveform, now this waveform is going to be a little bit different, because now you have the load here. Previously we were considering there was no load and it was an ideal situation, but practically you will have some load, and if that happens, then your the practical peak detection will be a little different than your ideal waveform, and that's why you see a little drop here, and that's due to load. So there are multiple modification which is done to this circuit, but I'm just going to show you the final modification, this modified peak detector. And you can go through the notes. In notes I have thoroughly mentioned the other circuits which came in between this basic circuit and this, so you can go through that. Now in this modified peak detector circuit, you see that we have used two operational amplifiers, and then we have two set of diodes. Input is given through this, and in the middle you have this capacitor, and then resistance is connecting through the input of the one op-amp to the output of the second op-amp. So Q1 and Q2 are your two op-amps. Okay, now let's take two cases. In the first case, your input voltage, which is this, when this input voltage is higher, when you supply some input signal to the Q1 op-amp, then in that situation what will happen, and then this is your input voltage Vin is positive. Okay, and right now the current going in here from here, this is 0. So you will get some output voltage here, and due to that what will happen, this D2 diode will be in the forward bias mode, whereas this diode 1 will be in reverse bias, because if you see that this is the negative side of the diode, and if you give some positive signal here, then this will be reverse bias, whereas this is going to be your forward bias, which means this will be turned on and this will be turned off in that condition, in that case. And once this is forward bias, then what will happen? The capacitor will start charging up. So whatever the input voltage you have given, then capacitor will basically charge to that value, and it will try to hold that value. Now in the second case, what will happen when your input voltage is lower, which is, let's say it is lower than this particular voltage, which is VP. When this input voltage is less than VP, then what will happen? Then obviously this is your, if this is your higher voltage, then this is going to be your forward bias, and then this D2 diode will be reverse biased. So in the second case, your this D1 will be forward biased and D2 will be reverse biased, and in that case your outer circuit will be broken, and the negative input terminal of the Q1 will be at the peak voltage. Okay, and the output of op-amp Q1 will be negative in that particular moment. For that particular case, when Vin is less than Vp, then this Q1 output will be negative, and D1 will be forward bias and D2 will be a reverse bias. So this, when this D1 will be forward biased, it will provide feedback to the Q1, because this is connected in the feedback path, and that prevents your operational amplifier going into the saturation mode, and that's why this is connected in the feedback. So if you use this circuit will be much faster, and this particular is basically your another operational amplifier is connecting, which is basically it will hold up the voltage which you are getting here, so that constant voltage can be maintained. So that's the modified peak detector, and that's the end of lecture. Thank you so much for watching.